has that many columns, has too many columns, the one I find. Okay, well that's cool because you can just drop extra columns. All the interaction goes on between pairs of cells on pairs of columns. So if you've got a column that doesn't correspond to any factor, then clearly there's no possible interaction there, so you can drop it. Now, you look in each column, the column is going to have unique numbers in it, usually starting at 0 and running up to 6, 7, 8, 9 potentially. So there have to be at least enough unique numbers in the columns to hold the options that you've identified for each factor. So if you've got 5 options for one of the factors, and yet there's a maximum of 3 or 4 numbers in the columns, again, forget it, it's not going to work. You're going to have to get a larger one. You got to get one that has enough numbers such that you can uniquely replace each number in the column with the name of the factor, or name of the option, excuse me, for that factor, and you won't run out of numbers before you run out of factors. Now, what sometimes happens is you identify an orthogonal array that's got too many numbers. Okay, no big deal. Once you've run out of the numbers, in other words, you've covered all the options that you need to, then the other quote-unquote spare numbers can be really done with any of the valid options. There's no restrictions here. It's tester's choice, as I say on this slide. Okay. Now, this last qualification is actually really unnecessary in the sense that if you meet the first 2 qualifications and you're looking at an actual orthogonal array, this third qualification, the third major bullet item here, will automatically be met. There will be at least as many rows as the product of the 2 largest number of options for the factors. So in other words, let's say you've got 4 factors. One has 2 options, one has 3 options, one has 4 options, and one has 5 options. Well, you would need to have an orthogonal array that had 4 columns, 5 numbers in each column. Usually there's the same number of numbers in each column, so it's 5 numbers in each column. And you would have to have 20 rows at least, though it would end up, if you had 5 numbers in each column, it would end up being 25 rows at least because of the fact that you now have 5 times 5. But you'd have to have at least 4 times 5, which was the number of options for the 2 factors that had the largest number of options. That sounds a lot more confusing than it works out to be in practice. In practice, it works out to be fairly simple. Now, one thing to warn you about, if there are too many rows, you can't just drop them like you can with the columns, because what will happen is oftentimes there will be interesting pairs or singletons in a row, interesting in the sense that they're not covered in any other row. So you have to check to see if that's the case before you drop any spare rows. Now, this isn't always something you have to worry about. I just mention it so that you don't go willy-nilly deleting rows without worrying about, am I cutting away something I actually need? Okay, I got a submarined. There it is. Okay. Mouse pointer disappeared underneath something or another, but now it's back. Okay, so you've located an orthogonal array on the AT&T website. You have downloaded that orthogonal array. You're ready to go. So here is a 5-step, pretty much infallible and almost entirely thought-free process for mapping your testing problem onto an orthogonal array. First, if there are any extra columns, drop them. So if you have 5 factors, you got 7 columns, drop columns. Which columns? Your choice. You can pick any 2 columns. I would recommend, though, that you pick the rightmost columns in the orthogonal array, because those are the ones that are going to be changing the quickest. Usually it's a good idea to keep the columns that change more slowly, and those are the columns on the left-hand side of the orthogonal array. This process, by the way, this mapping of the testing problem onto the orthogonal array, is going to be a lot easier if the first thing you do with the orthogonal array that you downloaded is import it into Excel or some other similar spreadsheet. Excel is particularly handy because it has a wizard. If you open a text file, that wizard will open up, and it will allow you to automatically divide the columns in the orthogonal array that you downloaded into columns in the spreadsheet, which makes your life a lot easier, which, after all, is a good thing, making your life easier. Okay, so you've deleted the extra columns. This is easy. Now, insert a row at the top of the spreadsheet into which you imported your orthogonal array, and write the name of the factor on the top, or factors, right? The name of each factor at the top of each column, one factor per column. Okay? You can do this in any order you want, but usually you want the factors that are the hardest to change, those factors which have the options which take the most work to change, to be towards the left-hand side of the orthogonal array, because those are the ones that move the slowest. They change the least frequently. Okay? Again, entirely up to you where you put them, but that's my advice. Put the factors that are difficult to change on top of the columns that change the least frequently, which is usually on the left-hand side of the orthogonal array. Now, column by column, select the cells in the column underneath the factor heading which you added, and use the search and replace option, which in Excel is Control-H. Replace all the zeros with the first option. Place all the ones with the second option, all the twos with the third option, and so forth, until every option for the factor that you're looking at has been mapped onto a number. Now, at this point, you should run out of numbers exactly at the same time that you run out of options, or you run out of options before you run out of numbers. If you run out of numbers before you run out of options, you broke one of the rules on the previous slide, namely the rule having to do with the number of numbers in each column. Go back and get another orthogonal array that actually is consistent with the rules given in the previous slide. Now, at this point, you may very well be done. It's quite possible, but there might be some additional work that you have to do, especially if you were forced to select an orthogonal array that was particularly big. It might have some extra rows in it. So if there are rows that have a lot of numbers that were not replaced with options, then look and see. If you got a row that's all numbers and doesn't correspond to any of the options, it's completely extraneous. You can delete that one. If you have a row that has pairs in it, and you can convince yourself that those pairs of options for those particular factors are present somewhere else, then you can indeed delete that row. Or if there's partial overlap, you can figure out, in many cases, ways to combine rows together. The important thing is, remember, unique pairs or unique singletons have to be preserved. If you erase that distinction, then you lose the property that you're after here, which is making sure that you tested every possible pair. With step 4 done, if you need to do step 4, if there are any spare cells that were